Hello, good morning. Can you hear me?
Good morning, sir. Yes, we can hear you.
Okay. Can you see the screen chat?
Yes, sir.
Okay. So we will just see some questions that I wanted to discuss today. Uh, here we have two diagrams, right? So these are very typical diagrams that we have to consider when we learn about the isotope systematics of samarium, neodymium, and rubidium, strontium. This is the isotopic evolution of the Earth, actually, right? So these diagrams represent the isotope evolution of the Earth. So the question here is, given the following isotope evolution diagram, what do points A, B, C, D, and E in the figures represent? Right? A, B, A, B, C, D. Right? Okay. Sorry. B is here, right? So we have to. Okay, I'll remove this one. Yeah. B is here. Okay. So what are these points refer? What is A? A is the chondritic meteorite. So it is mentioned as chondritic meteorite is here, right? Chondritic meteorite is here. So that's the composition. So that means the primordial composition of the Earth. Primordial composition of the Earth is given in this diagram as here in this diagram. Just a minute. The primordial composition of the earth. That means the samarium neodymium composition. Neodymium composition uh, at the time of accretion. At the time of accretion of the earth, right? At the time of accretion of the earth, right? So, because this is the diagram with neodymium versus time, right? Don't get confused with the isochrone diagram. This is not the isochrone diagram. Uh, the diagram, this shows the time evolution, right? So A represents the neodymium composition of the bulk earth, actually. The bulk earth, the chondritic composition, because once the core has been separated from the earth, that means the metallic materials has gone away into the core. Everything remained was silicate, right? So that's why we call it bulk silicate earth. So sometimes it's called bulk earth also, right? So that is the at the time of accretion, right? Now point B, the point B represents the neodymium composition of the bulk earth at the point of differentiation. At the point of differentiation means so far from A to B there is no differentiation, because it is just the primordial composition. This is the initial primordial composition, and then you can see here the evolution. Evolution is here, uh, where you can see it's evolved until 3G, approximately 3G, right? We discussed at 3, approximately at 3G, there has been some event which took place, right? Some event which took place where the Earth started differentiation. Okay, Earth started differentiation uh, at this point, right? At this point, it started differentiation. So this is the point where the differentiation started. B. After evolution, constant evolution up to like 2 billion years, right? 4.5 billion years is the time of accretion. It's here. And from there until like 3, right? Nearly 3, 1, yeah, nearly 2 billion years of 1.5 to 2 billion years time of evolution. Right. So from there, the Earth started evolving, and you can see the differentiation point as the B, right? So for the B point B represents the differentiation point, and C is here, right? C is here. It's what is the age of C? It's here, right? Age of C is the 0, 0 GA. That means today, present day. So C represents the present day neodymium composition of the rock, right? Uh, don't think about this igneous rock. It is just the earth mantle, right? Because after differentiation, uh, two mantle and crust both, right? Two differentiation lines are there, right? So one is here and the other one is here, evolution, right? Two evolution lines. That means this line and this line. So after differentiation, what happens to the mantle? Neodymium compared to their relative incompatibilities, samarium and neodymium. Samarium is more compatible, right? So it goes much into it remains much in the mantle rather than going into the melt, right? So uh, what happens for the neodymium isotope systematics? There will be a lot of samarium accumulated over the time that makes neodymium isotopically, radiogenically generated neodymium content to get increased with time, right? So that's why after this evolution time evolution point B, you will see high concentration of neodymium for the depleted mantle here, right? Otherwise the bulk earth composition should continue, right? The bulk earth composition should continue like this. Is just an extrapolation, because no longer bulk composition is there, because there has been differentiation at point B. So the melt which gets depleted in samarium, so over the time relatively it should get low amounts of neodymium isotope compared to the mantle. So therefore you will see an evolution like this, a slow what do you call not steep slope, gentle slope, right? The reason is less amount of samarium there compared to the mantle. Mantle, you have a lot of samarium, so the gradient or the slope is very high. It doesn't mean that continental crust will not increase its composition. It increases its composition, but the degree of increase is not as big as in the mantle. So still you have a positive slope here, but the angle, if you take the tan theta or the gradient, which is smaller, right? Here the tan theta is smaller, right? But here you have a bigger tan theta, bigger gradient there. Right. So that is how the differentiation is taking place, and these points represents that matter. And the point C is the present day. That means is 0 here. The present day isotopic composition of the melt. Actually, this is the continental crust. Actually, this should not be written as igneous rock. It's of course igneous rock, but it could have been written as the continental crust. Right. So here is the continental crust. You can see the melt represent the enriched melt. Here it is written as enriched melt. That means the continental crust, definitely, right? Enriched melt crystallized as the continental crust later, right? And then point D. Where is point D? I can't see that. Okay, point D is here, right? Point D is here. At this point, so point D is here, right? Point D means what? Present day neodymium isotopic composition. Present day, that's here because we are referring to this axis. Sorry, this point 0, and the value given is this value given is the present day neodymium isotopic composition of the mantle, right? Because that is the mantle. Because you can see here the mantle mantle evolves there, right? So actually in this diagram there is a small wait a minute, residual mantle. It says the residual mantle that differentiated from the chondritic mantle at point B. It has a positive value. Well, yeah, residual mantle because the continental crust formed. Then what you got was what you have remained with was the residual mantle, right? So the residual mantle, that is the depleted mantle. So residual mantle is coming over here and evolving, but they have mentioned here another event, right? So ideally this, just a minute, ideally this can't magnify. Okay. This D refers here. This there is a little problem in giving this name here. So this D should be here actually. D. It is the point where this line hits, sorry, this line hits the 0 G axis, right? Remember this line continued. You can extrapolate it up. Oh, sorry. You can extrapolate it up to. Well, I'll take the different color. You can extrapolate this line up to a point like here, so that you hit it. You hit the 0 MA axis, right? So D refers here. So D should be here, right? Because here at this point, particular point, that means about 500 million years, 0.5 GA. There has been an event. There has been an event recorded in this diagram where a basalt has been formed. Most probably, this basalt is a. Can anybody tell me? Because it is produced from the depleted mantle. So then, what should be this basalt? A typical basalt. What could be that basalt? Quickly, somebody tell me. Yes, quickly, somebody tell me. You know already. We have learned about types of basalts already. After the continental crust formation, what happened to the mantle? It became depleted. So now depleted mantle. This is a depleted mantle evolution curve, right? After continental, this is continental crust. This is continental crust because neodymium concentration is low. This is continental crust, and this is depleted mantle. And what is the depleted mantle producing basalt? Where do we get basalts? Sorry, I don't hear you. Yes?
Mid-oceanic basalt.
Okay, that's right. Very good. Mid-ocean rich basalt because that is the product of depleted mantle, right? Not oceanic island basalts, not OIB, right? It is a product of lower mantle, which is believed to be undepleted. Okay, a lower mantle, we believe it's almost like the chair composition, right? If it is lower mantle, then the basalt should be like this. Okay, OIB, because the lower mantle composition we assume more or less similar to this undifferentiated mantle or the primordial compositions. But upper mantle, depleted upper mantle is here, that can produce a basalt. Okay, so that can produce a basalt, and that basalt will be further kind of depleted and you will have some kind of uh, mid-ocean ridge basalt produced there, right? So if continental crust, sorry, if the continental crust started to differentiate again, I mean another event, if it gave rise to another event, that means at the same age, suppose here it's mentioned as a point here, right? If it's melted again, that means remelting. For example, migmatite formation, it's crustal melting. Okay, so this continental crust, this is the continental crust evolution. If crustal melting occurred, you can expect the continental crust to produce uh, a magma, right? A melt. So then you can have another one like this. Okay. So, but anyway, here you are given as basalt. That should be the mid-ocean ridge basalt. So, if you can put another letter here, E. Suppose you put E here, then this E should represent the mid-ocean present day isotopic composition of the mid-ocean ridge basalt. MOB, present day MOB. Okay. Sorry. That is the present day MOB. Okay. So anyway, according to this diagram, D represents the present day neodymium composition of the D represents present day neodymium composition of the residual mantle. Okay, residual mantle differentiated from the contradict, because this is the point of differentiation, right? Now, uh, now I want to, before going to the next section, let me share another document. Just a concept, because I think I haven't given you this at that during the lectures. I forgot. I just now reminded that. Okay, here you see uh, the relationship between the half life and the relationship between the half life and uh, the decay constant. Have you discovered it? Have you found it? We didn't discuss this. The relationship between the half life and the decay constant. Actually, half life is what? Time for half life, half the parent atoms to decay, right? That means how much you had initially, and when it becomes half, the time taken for that phenomena is half life, right? So that is years, number of years. But decay constant we are getting as per year. This is the unit of the decay constant. The relay, because you see here decay constant, the formula for the decay constant is this one, right? For the decay constant, ln2 divided by half. So this is, I mean, beyond your content of the syllabus to discuss how this equation was derived. But just keep in mind, a natural logarithm of 2 divided by half, divided by half life will give you the lambda, right? So you are getting lambda as a constant. All the all the time you get when you get a question, you will definitely get the lambda, right? You don't have to find the lambda. But in case if you are given the half life and then you are asked to find a answer to a question, you might need some sometimes you might need the decay constant, right? If you are not given the decay constant but you are given the half life, in that case you have to calculate the decay constant, right? Calculating the decay constant is based on this formula. So inversely you can interpret the half-life in terms of decay constant also, but it is not useful much because we know what is half-life is, right? So remember, lambda equals ln2 divided by the half-life. That's why you get different decay constants for different isotopic systems, because half-life is different. Okay, so if you want to define the half-life, maybe you can define it as the probability per unit time that an atom will decay. Probability, it's a kind of a probability. Probability per unit time. This is the unit time. This half-life is the unit time, right? Probability of the probability per unit time that an atom will decay. That is how the lambda is defined, right? Decay constant is defined. We took it just as a constant just to remove the proportionality. Remember, we were formulating the equation which involves decay constant, right? For geochronologic equation, the initial isotopes and then present day isotopes plus E lambda plus 1, like that, right? The y equals mx plus c type equation for the isotopic system, isochrone equation. For that, in defining that, when defining the radiogenic component, we just removed the proportionality symbol by introducing a constant. That constant we termed as the decay constant. So this is how the decay constant was uh, uh, how decay constant can be calculated. Okay, so just to keep in mind that as well, because sometimes you might get a question where you are given the half-life but not the decay constant. So then you can't run here and there finding the decay constant. You can just calculate it like this. Okay, right. One more thing I have to tell you, which we didn't have a time to discuss the problems. Another important point need to be given you. Okay, can you see the screen? Can you see the screen?
Yes, sir.
Okay. Right. So when sometimes you are another situation is there when problems are there, right? When you are asked to solve problems, sometimes you might not get the parent-daughter isotope ratio as a measured value due to various reasons. There are situations where you don't get the parent dot isotopic ratio measured because some instruments might have limitations, or sometimes the measured value might have a big error. In that case, you can just calculate it. You can just calculate it, but you need to know very precisely the composition of the elements. For example, if it is samarium neodymium system, you need to know samarium concentration of your sample, and also the neodymium concentration of your sample. That is an essential uh, essential factor that you need to know. If your machine or if your data sheet doesn't provide you the parent dot isotopic system, right? I mean isotope ratio, because if you use the isochrone equation, you need to know the parent daughter ratio also, right? Present day neodymium isotope ratio equals initial ratio plus initial ratio of the neodymium plus parent daughter ratio into uh, lambda lambda term, right? M lambda 1, sorry, m plus 1, right? So that for that you need to know the parent daughter isotope ratio, right? What samarium to neodymium isotopic ratio, 147 samarium to 144 neodymium. So in that case, what you have to do is you need to know the precise concentration of the samarium and neodymium. Actually, before embarking for any isotopic analysis, you must have a robust set of data with your trace elements and rare earth elements. That's why anybody, if you want to do age calculation, first you are asked to find out the concentration, right? Without the concentration, they don't allow you to do the measurements for isotopes, because isotopic measurements are very expensive, right? It involves a huge amount of money. I mean, the consumable cost is very high, machine cost is very high. Therefore so therefore any lab doesn't allow you if you don't have precise isotopic composition, and also the lab prefers to have to have this elemental composition also from their lab itself. They might not, or they may be reluctant to accept other labs values, because they want to rely on their data right? This is a kind of an ethical, not an ethical, but really very important aspect that you have to consider if you are a laboratory manager, for example, right? If you are accepting anybody's data and you do measurements for others utilizing those data, uh, you can't guarantee about your result also, because you are based on somebody's else data, right? So if there has been a mistake there, your data will also, I mean your production of data will also have some errors. So they can't be responsible for that. So therefore they prefer to have at the same time to measure the trace element composition also. I mean, at the same time means just before isotopic analysis you have to do the trace element analysis. But nowadays there are some improved machines, further improved machines, where you get this parent daughter concentrations also at the same time where you measure the isotopic composition. In that case, no problem, because you are getting the precise trace element composition, uh, precise elemental composition as well. For example, laser ablation machines can provide you all the RE data, all the rare earth element, not only just this samarium neodymium, but all the REs can be provided. So anyway, if you are given the samarium and neodymium isotopic composition, then using those data, sorry, samarium neodymium elemental compositions, that means ppm values, right? ppm values or ppb values, you should be able to find out the 140. For example, if you are given samarium composition, right? That is the concentration of samarium. For example, in this case, samarium 0.580 ppm. 0.580 ppm. So to calculate the parent ratio, we need 147 samarium. Okay, we don't know how much 147 samarium is there, because you are given only overall, because you have multiple isotopes for samarium, right? You have abundances, you have different amounts. So therefore you need to know exactly how much 147 samarium is there, right, to calculate the 147 samarium composition. Okay, so because since this is ppm means parts per million, but it's better that we convert it into the gram value. We can convert ppm into grams. How can you do that? ppm 580 0.580 means 508 0.580 milligrams, right? So ppm equals milligrams. Okay, so that means 5.80 into 10 to the power minus 4 grams. In gram, if you take it in grams, this is the amount. Okay, right. And also remember this notation here, samarium 0.580. Why? This is just 0.58, right? 580. It's written as 580. Why is that? Can anybody tell? Because this is actually, this is not geology, this is chemistry. This is about the concentrations and concentrations and the what? The the what do you call it? The machine precision, right? The machine can give you distinguish whether 0.581, 0.582 or something like that. If you are giving this as 0.58, nobody knows whether this is a rounded figure, right? If this is a rounded figure, then also you will have this 0.58, right? But this means uh, it is not a rounded figure, but this is a precise value 0.580, right? That means some samples might have 0.581, right? So it specifically says that this is not 0.581 but 0.580, right? So that is the precision, the precision of the measurement, right, up to the third decimal point. So that means up to the third decimal point you can have the precision in very simple terms. Okay, anyway, so once you have this ppm amount in grams, how can you find out the moles of samarium? Because isotopic abundance is given in calculated based on the mole amount, right? Not just the ppm amount. So therefore you can't simply consider the ppm amount and the isotopic abundance to find out the amount of each isotope there, right? So you need to know the mole amount. So how can you find out the mole amount? The ppm amount can be divided by the atomic weight of samarium. Atomic weight of samarium, that should be given to you. Atomic weight of samarium is 150.36 gram per mole. Okay, so you divide it and then you get the moles, amount of moles of samarium in your sample, right? Still we don't know about the 147, right? So now we know overall amount of samarium there in the sample, and now we need to calculate the amount of 147 samarium there. Now we know the mole, and then what do we need to calculate the amount of 147 samarium in the rock? Can anybody tell me?
Mass spectrometer.
Sorry?
A mass spectrometer.
Mass spectrometer, you can get the measurement. I am not asking that. I am asking how to calculate. Because I said the parent-daughter isotope ratio cannot be, there are instances where the parent-daughter isotope ratios cannot be given by the mass spectrometer. Right? In such a situation, we are dealing the question like this. You know only the concentration. So in that case, how can you calculate the 147 samarium? That is what we are doing now. Okay. So now
We need the relative abundance of
okay.
isotope.
Yeah, that's right. Very good. So we want to find the relative, we want to get the relative abundance of 147 samarium, right? We know the mole amount. That means that is the amount that you have, irrespective of whether it is a kilogram or whatever. The amount of moles in your sample you analyzed is this much in moles, right? Because we divided it by the atomic weight and got the mole, right? So now we have the relative abundance. We need the relative abundance of 147 samarium, and then we we get it by multiplication. Suppose it is 15%, the relative abundance is 15%, then what you do it, here you have to do 3.857 into 10 to the power minus 6 multiplied by 15%, right? Then you get the 147 samarium uh, amount, mole amount in your sample. Okay, so this is also one extra calculation that you might have to do in places where you are not given the parent-daughter ratio. So the 147 samarium to 147 neodymium also you have to find out. I mean, the 147 neodymium also you have to find out in a similar way based on the neodymium ppm value, right? Similarly, you have to calculate that, right? Okay, so I think this is clear for all, right? Isotopic abundance is necessary. And also there are situations where isotopic abundance is used to calculate the atomic mass also, right? In inverse way, in a reverse way, right? So once you have the isotopic abundance, and then you can back calculate and find out the atomic relative atomic weight also. That is also possible. Anyway, it is beyond our content, so we are not discussing about that now. But these points you keep in mind, right? Any question? For the radiogenic product, there is no way that you can calculate it, right? If we can calculate that, then we don't need any mass spectrometer, right? We can't do that. We need the mass spectrometer for that radiogenic amount. But here what we were discussing was the parent-daughter amount, because sometimes if the rock has because these parents and daughters isotope daughter elements might have been affected by some later process also, right? Which we may not have counted, right? But when you get that isotope ratio, uh, you might not get the real value. I mean the very precise value also. But nowadays many machines give that. But there are some instances where you need to cross check whether this is really consistent with the concentration also, right? So in that case, the machine given value could be compared with what your calculation here, right? Machine given value, you keep it there, and you do the calculation also using the accurately measured elemental composition, and you calculate it like this by mole, by dividing the molecular mass. Like that, you can uh, do the do the comparison also, right? So there are some situations you might need, but for rocks like uh, yeah, actually that needs if your samarium and neodymium concentration is very low, uh, uh, I mean, if your sample has very low concentrations, then you may need to you may need to you may need to calculate the parent daughter isotopic ratios by a manual method like this, right? Because when it comes to very low concentration, the atomic or the ion counting in the machine might not give you the precise data, but the ppm values will be given very precisely. So therefore you might need to cross check. Anyway, all these things are beyond your content. So we are at this level, we are considering everything is perfect, right? So this is anyway another another situation that you have to know. Let's go back to the questions now. You can see here. Hmm. Okay, so let's move on to the other questions. Right. So A, B, C, D. So that describes your situation there. And now, uh, you can see here another question. Given, sorry, we finished the above thing. And then given the following two isotope evolution diagrams, that means the two diagrams that we considered before, right? These two. Isotope evolution diagrams explain the differences in the two isotope systems. Explain the differences in two isotope systems. So we have neodymium isotope diagram and strontium isotope diagram against the time. So you are asked to explain the differences of these two diagrams, right? So what are the differences that you can expect, that you can find there? Okay, let's see. Okay, first one, the top diagram, that means the first diagram, the neodymium isotope diagram. The top diagram shows the neodymium isotopic evolution, in which the Earth starts out with the chondritic neodymium and samarium neodymium composition. Here, why? This is chondrite meteorite, right? You are specifically given that this is a chondrite meteorite, right? There can be so many other types of meteorites also, but we consider chondrites as the building blocks of the Earth, bulk Earth, right? So this neodymium diagram specifically mentioned that this is the chondritic meteorite, right? So that means the initial isotopic composition of the chondrite is given here. So this diagram shows the neodymium isotopic evolution in which Earth starts out with a chondritic neodymium and samarium composition, because it is given as chondrite, so definitely it should be the chondritic composition, right? Neodymium and samarium isotope, whatever the isotope system you measure there, it should be chondritic, right? Subsequent to accretion, the Earth differentiates a crust and mantle, with the latter having superchondritic samarium neodymium value. Okay. What is it saying? Subsequent to accretion, that means after the accretion of the Earth differentiates a crust and a mantle. A crust and a mantle, with the latter. What is latter here? Mantle. Okay. Earth differentiates crust and mantle, with the latter having a superchondritic samarium neodymium value. What is superchondritic? Higher than the chondrite composition. Superchondritic means higher than the chondritic value, right? So higher samarium neodymium value is there for the mantle according to this statement, right? That is, on average, light rare element depleted composition. Okay, light rare element depleted composition. High samarium neodymium ratio relative to the Ch, which is represented by point D. Okay, let's see now. Right here, Earth differentiates, right? So Earth evolves after the accretion, and then what happens? Earth differentiates crust and mantle, with the latter having higher neodymium and higher samarium and neodymium ratio. Higher samarium and neodymium ratio. That means superchondritic. Superchondritic samarium and neodymium for the mantle. The latter means mantally. Okay, let's see here. Right. After B, what happens to the mantle? The evolution. After the differentiation, it produced two reservoirs. One is the continental crust, and the other one is the uh, depleted mantle. So the mantle evolves here with the superchondrity. That means greater slope, right? Greater slope than the chair. The slope of the chair is given here, right? So you can measure some tan theta in this chair line here, and you measure the tan theta of this line. It is much higher. So that is why we call it superchondritic samarium neodymium ratio. And for the crust, it is relatively low, right? Compared to the chondrite, it is low, right? So this is superchondritic, and the former having a the former having a subchondritic samarium and neodymium. What is former? Crust. This is crust according to this, right? So the former having subchondritic, that means lower than the ch, chondrite, lower than the chondrite. So chondrite slope is this tan theta. You take this as the tan theta, and the crust, or here the crust is having a lower angle here. Can you see this low angle? So if you connect B and C, and see the angle of that, which is lower than the crust, lower than the chair evolution line angle, right? That means subchondritic. So lower than the chondrite evolution, because you see here the chondrite evolution is here. Okay, the extrapolated chondrite evolution line is there, which is having a higher gradient, higher tan theta. So the mantle evolves in a superchondritic parent ratio, a samarium neodymium ratio, and the crust evolves in a subchondritic ratio. Because you are asked to describe about these figures, and what you understand by these figures matters to describe. So that's why we want to see these things as very important points. Okay, and then low samarium neodymium relative to Ch, which is given in the point C here, right? So you have a low angle, low evolution line, low angled evolution line, right? The bulk Earth continues to have a chondritic composition. That is the extrapolation from point B, which marks the point in time to the differentiation events. Sorry. So extrapolation. So from point B, you can extrapolate it. You can extrapolate it and continue, right? If nothing happened to the chondritic meteorite or the Earth will be having a composition similar to this point today. This is the present day value, right? Here is the present day value 0 GA. So Earth should have been having that value if nothing happened. But at point B, there has been an event, right? There has been an event, crust and mantle differentiate. That means crust mantle formed. Therefore, Earth is no longer having the chondritic composition. Okay, that is what you have to explain. And then about the second diagram, the bottom diagram, that means rubidium strontium diagram, strontium diagram against the time, the second diagram. The bottom diagram shows the strontium isotopic evolution in which Earth starts out with a chondritic strontium ratio and a non-chondritic rubidium strontium composition. Non-chondritic rubidium strontium composition. The Earth has chondritic relative abundance of refractory elements, including strontium. Okay, first let's see the diagram. Okay, it says a meteorite. It says just a meteorite, but you are not given it as the Ch. Here you are given it as chondrite meteorite. But this is just a meteorite. We don't know whether it is chondrite or not, different meteorite or not. Okay, but you have to consider a fact here. The Earth has here this line. The Earth has chondritic relative abundances of refractory elements. Refractory elements means the elements which are not easily incorporated into a melt or vapor. Into a vapor or melt. That means they can't easily get evaporated, right? Strontium like elements, they don't get evaporated easily, right? Even samarium neodymium, they don't get evaporate easily. But the elements like rubidiums, potassium, sodium like things, those are considered as low refractory elements or volatile elements, right? Sometimes these are called volatile elements, even lead like elements, right? Volatile elements, they can easily be removed from the system into the forming a vapor, right? So therefore we have no trust on rubidium, whether they have rubidium ratio should have been there as the chondritic composition. So that's why it is considered as non-chondritic rubidium strontium composition. Okay, but chondritic strontium composition means because strontium is refractory element. So here uh, we can assume strontium should have been similar to the chondritic composition, but the rubidium composition should not have been there chondritic, right? Although rubidium is not indicated here, but we need to have the rubidium strontium ratio for this slope determined by rubidium strontium ratio, right? Like here in the first diagram, the slope determined by samarium neodymium ratio, right? That is parent daughter ratio. Here also you need the parent daughter ratios, parent daughter slope ratios, yeah, right? to find out the tan theta. Okay, but since rubidium is a highly volatile element, we don't know whether it represents really the chondritic abundance. Okay, so that you have to know, that is a fact that you have to know if you are not given it as a chondrite. If it is chondrite, then probably you can assume everything is chondritic, but since this is not given, you can consider that it is non-chondritic. Okay, we don't know, that's why. Okay, Earth does not have chondritic proportions of rubidium strontium. Consequently, Earth does not have chondritic proportions. That means Earth is not having quantity proportions, because if rubidium is has changed, being it a volatile element, then you can't expect the quantitic rubidium strontium value. Okay, right. So on average, crustal rocks have high rubidium strontium values, and therefore evolve to high strontium isotope values. That is obvious, right? Because rubidium is highly incompatible, right? Not only volatile, it is highly incompatible. These are two things: volatile and incompatible. Incompatible means the preference to a melt or a solid, but volatile means the incorporation into the vapor, right? I mean, being evaporated, possibility of being evaporated. That is the volatility. Volatile nature, the nature of some alkaline elements, right? So anyway, uh, since this is incompatible, rubidium is an incompatible element, you will definitely have high rubidium concentration in the crust. So therefore you will have high rubidium strontium ratio, which we have already discussed in the class, to have high strontium isotope ratios for the crustal rocks, right? Right. So how it is shown here? Evolution, sorry, evolution of continental crust, because it must have a high tan theta, higher tan theta compared to the original evolution. Original evolution here, tan theta is lower angle, but here the continental crust after the differentiation around 3 point GA, similar to this event timing, 3 point GA at the same time. Crust is having high strontium isotope ratio, because it has high rubidium amounts fractionated or partitioned into the crustal composition, into the melt, right? Residue has less amount of rubidium, melt has high amount of rubidium. So with time it produces high strontium 87 ratios, strontium 87 products, because rubidium strontium parent daughter ratio matters for uh, isotopic radiogenic decay. Okay, so crust is having a higher slope, but in neodymium mantle is having a higher slope, right? So that is the fact that we have already discussed in other sections in the class. So the mantle, the depleted mantle, rubidium depleted. Here you can say specifically rubidium depleted mantle, because we are considering rubidium and strontium here. It doesn't matter. So rubidium depleted mantle evolves with a lower tan theta, lower angle. If nothing happened, the meteorite should continue to evolve in a line like this dotted line, broken line. Okay, right. Okay. Then, whereas the depleted mantle has on average low rubidium strontium and low strontium 87 to 86 values, right? This one, because it has less amount of rubidium, so you are getting a lower slope, right? So this is what you have to explain if you are given this question. The following isotopic evolution diagram, what points A, B, C, D, and E in the figure, and describe about the figure. Okay, here given the following two isotopic diagram, explain the differences in two isotope systems. So that is the two differences you have already discussed here: subchondritic, superchondritic evolution, like that. Sorry. And non-chondritic evolution, because rubidium is a volatile element. So if you are no longer considering any volatile elements, then in for meteorites you can consider they must have the chondritic composition. I mean the similar to similar to the chondritic uniform reservoir, because all the meteorites do not comply with the chondritic composition, because they may have uh, subjected to different processes. We don't know those processes, right? If anything volatile is there, they can be highly such elements can be highly affected. Okay, so the other one, how might these systems, the other section, how might these systems differ if one used the evolution of the depleted mantle? If one used the evolution of the depleted mantle as a reference frame instead of the Ch reference frame. Here we consider the Ch reference frame, right? So if you can use a depleted mantle reference frame, so in that case, for both using a depleted mantle reference frame, for both diagrams, we'll still begin with the same starting point. Because, you know, whatever the things happen to the earth should matter, right? Depleted mantle formation is from B onwards, from point B onwards, right? Irrespective of whether it is a chair or I mean, whatever the system that you consider, you should have the depleted mantle formed first of all, right? So the formation of the depleted mantle is at the point B. So ideally, the starting point is same. Only difference is you may not have this chair evolution section because you are no longer considering the chair. But actually having that also no problem because the chair is the chondritic meteorite is the parent or primordial composition to form depleted mantle. So therefore, there is no harm to have this here, right? From here onwards, from B onwards, point B onwards, you are considering the depleted mantle. So starting point is same, but its evolution would start at the first melting and differentiation event time, right? So you might consider its evolution as starting from here. That is what I mentioned before. You can delete this section, right? You can delete this section, but it is not necessary. You can have that also, but it doesn't matter. You can just start with this point B onwards, showing the depleted mantle, like this, and extrapolation like that. Actually, for extrapolation, you definitely need this line, right? Otherwise, how can you do the extrapolation? So you can keep all these sections as it is, right? Only thing is, instead of Ch values, you have to use the depleted mantle isotope ratios, right? Remember the model age calculation and all, Ch model age calculation and depleted model age calculation, like that we did. Okay, but its evolution would start from the first melting and differentiation. So the B is the first melting and differentiation point. So that's okay, that's correct. At that time, you still have three components. What is that? Depleted mantle, bulk silicate earth. You see, BSC, bulk silicate earth is the chair. So you must have the chair also here, right? So that is the second component, and continental crust, the third one, the extract, melted extract. So one depleted mantle, one, chair two, and the continental crust, three. Those three reservoirs are still there as it is, right? These three components will evolve with their characteristic slopes depending on their samarium, neodymium, and rubidium, strontium values, right? For those two diagrams. So evolution will happen based on the samarium, neodymium value. The same diagram you can use irrespective of whether you use Ch or depleted mantle. It doesn't matter. Only thing is the difference comes when you are to calculate the model ages. When you are to calculate the model ages only, these two reference frames to be considered. Okay, for the diagram itself, you don't need to consider anything particular differently. Okay, so model age equation, you have to remember the model age equation and uh, epsilon calculation equations, right? These are, because these are principles compared to how much your sample in a neodymium composition. That is what you get from the epsilon neodymium value. And model age means the timing is not the absolute age, but the timing where your rock parent material separated from the crust or mantle or whatever mantle, from the mantle, sure, right? Model age. So that is very necessary. So you remember those diagrams, okay? Right. So here only thing is if you consider the model age calculation, then you have to use the relevant reservoirs isotopic ratios. For Ch, if you are using the model age with respect to the Ch, then you have to find out the Ch values for present day and Ch neodymium ratios, Ch samarium neodymium composition, like that. All these data are given, right? These data will be given to you, but sometimes you might need to calculate some values if you are not given based on what we discussed previously, right? In previous slides, I told you that if you are given half-life without the decay constant, then you should know how to calculate the half decay constant by using the half-life, right? ln2 divided by half-life, that is the decay constant. And then if the parent dot isotope ratio is not given, or it said maybe it says not measurable or not precise or something, then you have to use the precise trace element components, trace element composition of samarium neodymium or rubidium strontium to calculate the parent dot isotope ratios, right? Like what we discussed just a few minutes ago, right? You divide the concentration by the molecular mass and then multiply by the abundance, atomic abundance, right? So these are very principal, I mean very basic concepts that you need to know, right? Okay, right. So another section of this extension of this question, here you are given like this. Okay, it says sketch a likely chondrite normalized RE pattern for the residual depleted mantle, continental crust, mob, and chip. Okay, sketch a likely chondrite normalized RE pattern. Like it is not, you don't need to sketch precise diagram, but it can be a likely diagram, right? Likely sketch. That means a simple sketch, right? Considering the behavior of light rare elements, because and heavy rare elements in these reservoirs, because you know light rare elements are highly incompatible. Heavy rare elements are compatible relatively. Okay, right. So if you consider depleted mantle or continental crust and shear, you need to know how these can be variable, right? Okay, so if you sketch, it will be shown like this as a normalized concentration, because you can remember these diagrams, trace element abundance diagrams, you have to normalize it, right? Normalize, otherwise you don't see a smooth pattern, otherwise you will see a zigzag pattern, right? So once you normalize, that's why you have given this y-axis as ordinary chondrite normalized concentration. That means your sample concentration ppm value is divided by the respective composition of that element of the chondrite, right? Chondrite values are known, those are standards. We have standard values, so we have known values. For example, samarium chondrite value might be there, then your samples chondrite value, samarium value, should be divided by the chondrite samarium value to get the normalized composition. So like this, you can have this diagram. So if you draw this diagram, you will see depleted. Okay, let's see the depleted mantle first. Depleted mantle. So actually by the name itself, depleted means incompatible element depleted, incompatible element depleted. So incompatible element depleted means the light rare element depleted. So in that case, in this diagram, you must have light rare element depleted pattern here. light rare earth element depleted pattern here, like this, right? Okay, so you can draw it like slightly uh, bulging downwards and more or less very flat. This red curve, I am referring to the red curve, depleted mantle, right? Middle to heavy rare earth elements are more compatible than the light rare earth elements. So therefore, these depleted mantle, that means it has already contributed the melt to the formation of the continental crust, right? Or mob, whatever, right? So melt has uh, escaped anyway, right? Melt has escaped anyway. So sorry, it should be mob, right? Not the continental crust, because continental crust formed first from the bulk silicate earth, chondritic evolution, right? So mob is produced by directly by the depleted mantle, right? Depleted mantle, the mob is directly produced by that. That's why we consider here, see, here basalt. This basalt means the mob, right? So depleted mantle contributes to formation of the mob, and the bulk silicate earth or the chur initial composition contributes to form the continental crust here, right? Don't get confused. Continental crust formation is here and mob formation is here. Okay, right. Okay, so what is there? So light rare earth elements are depleted in the depleted mantle. So you have to draw like this. So typically, thousands of data have been plotted and found that it's around one. Around one, these values are recorded, right? That means heavy to rare, what middle to heavy rare earth elements. It's variable between, I mean, one or two, like just around one, right? But the depleted, the light rare earth elements are below one. Light rare earth elements are below one, right? So the concentrations are below one, but it doesn't this is a logarithmic scale. So this is 2, 3, 4, 5, 6, 7, 8, 10. Yeah, it's like 0.8, like this area. So you can draw like this because these are standard values. So it will be giving all, wherever you sample depleted mantle, you will have similar type of a behavior. Okay, right. And then we'll move to the green one, that is mob. That is mob. Mob, it is given as N mob. N mob means normal mob. Actually, mob also has two categories, three categories: normal mob, enriched mob, and depleted mob. Right? N mob, E mob, and D mob. There are three such components that you don't have to consider much, because the mob itself can start melting in some cases, right? So that it will deplete further. It is of course depleted, but further depletion can take place. So then we call it depleted mob. Sometimes it might be enriched also due to various processes happening in the earth mantle. In that case, it is called E mob. So average between these E mob and D mob, we take as N mob, normal mob, right? That is a normal mob composition that we consider, standard mob composition, right? That mob composition, because it is melt, right? It is melt formed out of the depleted mantle. So this depleted mantle, this red one, gives rise to the mob, right? This red one gives rise to the mob. Depleted mantle forms mob. So definitely, once you are creating a melt, all the incompatibles available try to go into the melt, right? They try to go into the melt, fractionate into the melt, right? So even depleted mantle, although they contain less amount of trace elements, it doesn't mean that those elements will go into that, right? So ppm values will be high. So that's why you get higher ppm values than the depleted mantle for the mob, the melt that was formed out of depleted mantle. The protolith of the mob is depleted mantle. Remember, protolith of the mob is the depleted mantle. Right. So depleted mantle, while having a concentration like around 1, the mob will be having somewhere around 10. Right. That means mob is 10 times enriched than the depleted mantle. Mob is 10 times enriched in all elements, all rare earth elements listed here according to this diagram, than the depleted mantle. Right? These type of interpretations you have to give clearly. What you see from these diagrams is such kind of features, right? So you have to explain. So even NMOB has taken its parent pattern almost, right? Parent pattern, see, incompatible elements are depleted because your parent was incompatible element depleted, right? So mostly it takes that sort of a pattern. So it's a kind of a genetic relationship, right? But it's not necessary to have this type of same pattern because geochemistry has so many variations. But luckily for depleted mantle and the mob, they have same pattern, but 10 times difference in absolute concentrations, right? So remember, absolute concentrations are 10 times different than the depleted mantle values, although they have the same type of a shape in chondrite normalized diagram, right? And then the blue one, that is continental crust. You can where how the continental crust is formed. What is the protolith of the continental crust? That is the chondrite, right? Or chondrite, chondritic meteorites, right? So that is what happened here. So you can always remember this diagram so that it will make you easier to understand and also to answer questions. You remember this diagram, these two diagrams, right? So the continental crust was started to form at B, right? So from the chur. So protolith should be this one. Depleted mantle is coming over here and mob is generated at a later time. It is not necessary at 0.5, remember, right? It's not always at 0.5. It may be 2 GA. Also, you can have a mob. In that case, your line should be like this, right? Some angle still below gradient than the depleted mantle curve, right? It's not always 500. It can happen anywhere. But anyway, once you have a melt generated from the depleted mantle, that is the mob. Okay. Right. So the continental crust, because the incompatible elements are enriched, you have a pattern like this. You have a pattern like this. And then you can see some kind of heavy rare earth elements kind of a depletion. It's not really flat, but slight depletion is there. It can be flat also, but not necessarily to be flat because this is entirely formed from the melt generated from the chondritic composition. So heavy rare earth elements might be really fractionated in low quantities. So therefore, it can give a further depleted type of a gradient for the heavy rare earth elements, right? Heavy rare earth elements, unlike the real pattern, sorry, flat pattern you observe here for the what the chondrite or the depleted mantle, right? Okay, so continental crust definitely having, you see, very close to 100. That means compared to the depleted mantle, 100 times or 50 times maybe, right? Because 50 is around here. Above 50 times, above 50. It is above 50. 50 times greater in incompatible elements because they are heavily concentrated. So relative abundances you can understand here. For example, depleted mantle when light earth elements are around 1, right? Mob has 10 times greater, right? But the continental crust has above 50 times, right? Above 50 times. And, the heavy earth elements, like depleted mantle is very close to 1, right? Here, this one, around 10. Continental crust is around 10, even less than 10. Even less than 10, 8 times, 7 times, like, because mob is around 10. Mob is around 10. Mob is around 10, but the continental crust is further depleted. Remember, right? It's enriched, means enriched in incompatible elements, right? So these are the typical shapes of these reservoirs. We call them reservoirs: continental crust, mob, depleted mantle, chair, lower mantle. All these things are termed as reservoirs in the earth, geochemical reservoirs. Okay. So anyway, this is the likely chondrite normalized RE patterns. So being chondrite, if you draw the chondrite meteorite pattern, it should be where your sample divided by chondrite, right? That means chondrite divided by chondrite. That should be 1, right? But due to some reason, I don't know what reason was there, this particular chondrite C2. Okay. This normalization we do based on C1 chondrites. Okay, there are two types of chondrites: C1 chondrites and C2 chondrites. So this is also beyond your scope of the syllabus. If you are studying planetary physics or planetary sciences in deep, you will talk about C1, C2, carbonaceous chondrites, what else? Metallic or iron chondrites. Like, there are so many types of chondrites. So normally for normalization, we use C1 chondrite, right? So C1 chondrite is little enriched than the C2 chondrite. So that's why C2 chondrite is having less abundance than 1, right? 0.8, like. And if you divide this, if you plotted the C1 chondrite in this diagram, definitely you will have just a straight line here, like along the long one. Okay, that also you have to remember. This is C2 chondrite is plotted, which is slightly depleted in composition than the C1 chondrite. That's why you get lower values. Otherwise, the chondrite composition should be around 1, right? Because for normalization value, we take C1 standard values. C1 standard value. Okay, right now. Any question up to now? All these, I think all these descriptions should be available in the White's book also. W.M. White, I told you about White, right? So that book must contain these details. Okay, right. So then we'll move to the section question 2. Do you hear me? Do you hear me clearly?
Yes, sir.
Okay. Right. Question 2. Calculate the 143 neodymium, 144 neodymium ratio of CH, chondritic uniform reservoir, at 2.5 GA. At 2.5 GA, right? That means you are given the present day compositions. You are given the present day compositions, like. Can you write down this question also? Calculate the 143 neodymium, 144 neodymium ratio of Ch, chondritic uniform reservoir at 2.5 GA. Given that the present 143, 144 neodymium for Ch is 0.512. These are standard values. You are given this value, okay? And its samarium composition is 0.1967. The half-life of 147 samarium is 106, right? Okay, you are given here, see, that is lambda is this much. You see, both are given. Half-life is given, and you are given as that is lambda this much, right? From the half-life you can calculate the lambda. Okay, anyway, so you don't need to calculate the lambda now in this case, because you are given the lambda value also. Otherwise you should have calculated the lambda using the value ln2 divided by what, half-life, right? ln2 divided by half-life, that is the lambda value. Okay, please try this. Please try this question now quickly. Okay, it's a simple question. It's not very difficult. Can you tell me? Okay, maybe you can put in the chat box the answer. Each of you, quickly, please. Those who have completed. How many of you completed? How many of you have done that? Please put in the chat box your answer. The neodymium ratio of Sher at 2.5 Ga. You are given all the other data, right? Present day Sher composition is given, and what? The samarium ratio, that means parent daughter ratio is given, half-life is given, that means lambda is given. So I have received 2 answers. Okay, I'm receiving more. Okay, let's see. Okay. Yeah, some people have got 5.508. How come? කොහොමද ඒක ආවේ? Dilini's answer is 0.508. All others are having 0.509. Nipun has calculated up to 1, 2, 3, 4, 5, 6 decimal point. How did you do that? Just the calculator given answer, or you are somebody 5, no, Lahiru, 0.50939. Anyway, you can get this answer, but I'm not sure why this 5.508 came. 509 is the 509 something should be the answer anyway, right? 0.509, you check it again, because there may be some mistake somewhere, because the 0.508 I cannot accept. Okay, right, 5094, right? Yeah, so you have to be very careful about everybody has to be very careful about calculations, because you will lose the entire marks for that section, right? Because if you are not attaining the final required answer, you might not get the answers, marks for the section, right? Because these are very principal or very preliminary type of questions, right? So that's why. So there is no point of giving answers. If you are arriving at wrong final answer, that will be very disastrous. Okay. So therefore, that's why for the steps you might not get marks. But if you have only the final answer correct, then you will get the all marks. Okay. Right. 59509,395. Right. That is the answer given also by in this tutorial also it's given, right? There may be some slight variations in the 4th decimal point onwards, based on different calculations, it doesn't matter, right? It doesn't matter. 509, the next point we can consider. Okay, so, okay, right. Now, another point. If in case if you are not given this one, samarium neodymium, sorry, samarium neodymium ratio, what would you do? If like for example 147 samarium, 144 neodymium, ratio is 1967, right? That is also measurable, but I said sometimes you have to have a precise elemental data to calculate it and cross check with the machine given value is correct or not, right? So that is also important to cross check. Okay, so in that case what you are going to do, then you will need to have the samarium neodymium ppm amounts, right? Remember, you need to have samarium neodymium ppm amounts and then abundance and then calculate the ratio, right? For both 147 samarium you need abundance, 144 neodymium also you need abundance. After converting the ppm amount into molecular proportion, that means mole amounts, and then multiply by the abundance, you get the we get this particular ratio, right? Okay, so that's all for that question. But there is another simple thing that I want to show you. Just a minute.
Excuse me, sir.
Yes.
Sir, how can we decide the number of decimal points for the answer?
No. Yeah, it's a good question. For rubidium strontium or for rubidium strontium system, usually their concentrations are high. I mean, the numbers are high. So you can stop at 3 or 4 decimal point. It doesn't matter. But for samarium neodymium, lutetium hafnium, rhenium osmium, what else? Lead, you need to have at least 4 decimal points, right? It's not a, I mean, it's just a kind of a convention. So at least 4 decimal points you have to show in your, even if you present a diagram, it's better you go for that number, right? Rubidium strontium is also okay if you show 4 decimal points, but 3 is also okay for rubidium strontium only, because their concentrations are very high and the last decimal points do not change much. I mean, the error or the uncertainty might not affect much. This all depends on the uncertainty, right? We discussed this at the class about the uncertainty, right? Okay, so let's move to another question. Just last question. Okay, can you see the screen now?
Yes, sir.
Okay, right. So this is another one, also from White. So let me check, because we are dealing with only this isochron part. I mean, we are not dealing with the argon. I think you can remember there are argon noble gases also. There are radiogenic isotopes, right? We are not considering noble gas isotopes under the undergraduate syllabus. Okay, it's a different thing. Okay, so I'm looking for the question now. Okay, here the question is here. The following data was obtained on 3 minerals. I'm considering this one, right? Just a minute. The following data, this question was obtained on 3 minerals from pegmatite, from a pegmatite. So from a pegmatite, they have separated muscovite, biotite, and K feldspar, right? 3 minerals have been separated because mineral isochron data are very precise, right? Rather than you are going for multiple whole rock data, mineral isochron is the best because in the whole rock scale there may be some processes which are some processes or kind of metasomatism or something might have affected in micro scale that might not have been noticed to you by your thin section observation, but still that affects for the isotope ratio. So therefore it's better if you can separate minerals first and then do the isochron. So at least 3 points are necessary to draw a precise line, right? 2 points are enough for a line, but for isochron you need to know about the slope also. So therefore at least 3 points are necessary to draw the line. So that means three minerals are necessary for drawing that isochron, and also you can use the whole rock also to plot on the same diagram. That doesn't matter, right? So now we are given three minerals and their rubidium strontium concentrations, and strontium daughter isotope ratio is given, radiogenic isotope ratio is given, right? These are the measured values that we know. Calculate the age of the rock. Calculate the age of the rock using the isochron method. Using the isochron method. Once you are told to use the isochron method, then you must plot this in a diagram, in a graph, right? Then only you can draw you can find the age. Otherwise you have to use a computational method where regression method can be used, right? Excel, instead of a graph you can use a software or Excel to find out the regression line and then get the gradient and the intersection. All these can be taken, but when you are doing manually you must plot this in on a graph sheet so that you can get a precise value. In the graph sheet also you can get a very precise value, very close value to the computational method, but of course the very high precision can be obtained from software or Excel or other type of isoplot or some other program, right? Anyway, so these are the values we are given, but you see here you are not given any parent dot isotope ratio. Parent dot isotope ratio is not given. You just first check whether you are given the parent dot isotope ratio. If you are not given the parent dot isotope ratio, then you must have calculated it. So how can you calculate it? You have to calculate rubidium, strontium, uh, ppm amounts, divide by molecular weight, get the moles, and then abundance, and then relevant isotope ratios for rubidium and strontium. Okay, 87, 86, everything you have to calculate. Okay, right. So let's see. You see here, in order to calculate the rubidium strontium ratio, so that is the parent daughter ratio, right? It's not given there. That's what we just mentioned. Parent daughter isotope ratio is not given, so we need to calculate the atomic weight strontium for each. Then the fractional abundance of 86 for each sample, right? So you can't sometimes people might use very standard values, but it might not be possible to use standard values because these are mica. Two minerals are mica, the other one is a silicate, other feldspar. So mica contain a lot of rubidium and strontium compared to K feldspar, and also their behavior is different. So using standard values, there are some standard values for different reservoirs, but for example, if this is derived from the continental crust, you can use the parent daughter ratio of continental crust as an approximate value since you are not given that. But it's better to calculate because you are given the very high precision ppm values for rubidium strontium, so you can just simply calculate it. Okay, right. So how can you do that? So muscovite, so you can see this diagram. Muscovite, you have rubidium, right? ppm rubidium, ppm rubidium value, strontium, and then biotite, you have rubidium value, and okay, it's not quite okay. Biotite, you have rubidium value, you have strontium value, then feldspar, you have rubidium value, strontium value, right? So likewise, you can plot them. Sorry, you can use them to find out the molecular amount. So moles of rubidium here, the moles of rubidium 2.7. How can you get that moles of rubidium? This 238 should be divided by molecular weight of rubidium. You have to get the molecular weight of rubidium, right? That will be given. A chart might be given, right? Or in the lab there are those numbers available in the form of a textbook or a chart. So you take that and divide it. For strontium also you do the same, and you can get the number of moles there, right? And then number of 87 rubidium moles. How can you do that? How can you get that? Once you have this number of rubidium moles by division of rubidium ppm amount with by the molecular weight, you can multiply it by the abundance of 87 rubidium, right? Abundance of 87 rubidium, you can multiply this value so that you get this 0.77 something, right? So moles of strontium also can be calculated by dividing the molecular weight and then multiply by the 86 abundance value. So now you have 87 abundance, 87 moles and 86 moles. Then simply you can calculate the ratio. 87 rubidium to 86 strontium. 4 muscovite, because this is 4 muscovite, right? And also you can find out similar way. You have to have the 87 also, right? 87 also you need to have, and then find out the amount there. Okay, right. And then for biotite also you do the same. For the biotite also you do the same. You get the moles and then multiply by the respective abundance and get the oh, sorry, very sorry. This is given, right? This is the radiogenic daughter product, right? This is given. So you don't need to calculate, right? In that case, no mass spectrometers are necessary. This is the parent, this is the dot isotope values that you get here. This one, okay? Don't get confused. These are given, right? This is from the machine, but the parent data is not given from the machine. If you have been given it from the machine, you can directly use it. That's why we are now calculating. So rubidium strontium parent value we get. Okay, so now we know the parent daughter value, we know the present day value, the isotope daughter product we know. Then what you are asked to do was obtained from calculate the age of the rock. Okay, now age of the rock using isochron method. Now what you have to do, you have to put the isochron method, isochron diagram. So you have to plot these three minerals in a what do you call in a graph sheet, right? In a graph sheet you you plot them and find out the gradient I mean you have to use two independent points to find out the graph. So I saw some of you had used just the given points and found the gradient. That is not correct, because given points do not represent, I mean necessarily represent the isochron on the line, right? They might not lie on the exact isochron line. That's why we are having a regression line, right? The most reasonable line among the points, right? It doesn't mean that this line should go every points. Ideally it is good if you can draw this line as going through all the points, right? That is the ideal situation, but in practical You never find such kind of situation. So therefore, what we get is the best fit line or the regression line, right? And then using this line, you are calculating the gradient, and that gradient you use for age calculation, right? So simply you use the age equation. Age equation, what you are given here now, the strontium radiogenic product of strontium is there, daughter product is there. Now we calculated the parent, and what else? You need the lambda, right? You need lambda. Lambda should be given anyway. Otherwise, at least the half life should be given. So in that case, you can have the lambda there. Okay, here the lambda is given in this place. Lambda is given. So use that lambda and get the intercept and the slope. Intercept and the slope. So slope is 0.00163. Then you can equal it to E lambda t minus 1, that equation, that our isochrone equation, and find out the t. Find out the t, right? That is the age. Okay. So this is what you have to do. Once you are not given the parent-daughter ratio, right? Parent-daughter ratio is not given. So in that case, you use the molecular proportions and then the abundance. Then you do the calculation, right? In this case, actually, okay, age is given, calculated 114 million years. They have used a computational method, so that's why you have, even they have calculated the some abundances in different way, which you don't need to consider because it is a numerical calculation method, but we don't need, because we are given the isotope abundances already. They have calculated even the abundances, right? Even the abundances calculated, right? We don't need to go into that depth at this level, right? So anyway, you should plot these values in a graph paper, and you will have typically this type of isochrone, right? So this is the reason. So you see the middle point, which is not lying on the which is not lying on the line, right? So therefore, you subtract, even the first point does not lie, right? If you subtract y2 minus y1, x2 minus x1, like that, right, you will calculate some number, but not the real gradient of this line. To get the gradient of this line, you have to select some arbitrary points, 2 points on the line, and then you take the difference, right, to get the gradient. So that's why the best fit line is necessary, because the best fit line only gives you the real age, the correct age, right? So you can use some programs like Isoplot. You can search in the internet. You will have the free access to Isoplot, but not necessary for this level at this point, right? So manually do that to find out the age. Okay, so this is the content that I wanted to cover. Any question? Do you have any question? So please, okay. Yeah, no problem. Yeah, you had some chat box, right? Answers. Just put your registration number in the chat box quickly. Any questions? So maybe I can share this this PDF to you. But some questions are beyond your syllabus, so don't worry about those things, and you don't need to consider them, but just focus on these ones. For example, there is another one, another table is given, right? So there are P1 to P7 samples. There are 7 samples, I think, logopites samples, and rubidium strontium and strontium ratios are given. So you can calculate the age of the rock, right? Age of the rock, but don't consider, I mean, you are not supposed, sorry, you are not supposed to uh, discuss about the uncertainty of the urge. That is plus or minus how much you get, like, right? You can't get it manually. You have to use a computational method. So therefore, don't worry about that. But you can calculate the age. You can calculate the age, and also the initial ratio you can calculate. And don't worry about this uncertainty, right? You don't need to consider about this uncertainty. And and don't yeah, this one, uncertainty of the initial ratio, you don't need, uh, and also the other parts you don't need, the relative uncertainty or something, right? That's not necessary, because actually this is done through isoplot. So here this link directly takes you to the isoplot, right, by Ludwig, right? So you can get the isoplot from here, from this one. But Excel 2010 does 2010, right? It does not support, I think, right? Because isoplot is designed for previous versions of Excel, but still people are using. It might have some complications. I don't know why they are not updating it. They are just saying you use 2003 version, right? So if you have to use that one, then we have to have 2003 version. But you can try with the 2010 also if they have in case updated it. But there are other isotope plotting diagrams also, analyzing diagrams also, sorry, software also. But you don't need to bother about those things at this stage, right? So I will share this one, and you have all the answers also. So you compare it with your manual plotting, right? You plot them manually and you compare it with these computational values. Okay, you see the uncertainties are also calculated, that is by the software or the Excel program. You don't have to worry about that, but you can plot this one manually like this. Most probably it will form a very good isochron according to this diagram. This is the machine generated one, the program generated one. So you should also have a very good isochron line when you plot this data, right? So it all depends on the data quality also, right? If data are not in good quality, they must have been scattered. So then you are not getting a real age. Okay, anyway, so I'm going to stop now. So, screen is not shared. Okay, okay. Screen was not shared, right? But anyway, okay, I'll show you again. Where is it? Okay, I hope now you can see, right? Can you see? Can you see the diagram?
Yes, sir, we can see.
Okay, so this is what I was telling was that if it is a good data, ideally you must have good fit, right? Here it's not very good fit, but still you have some points very closely located. And why I asked you to take the gradient from the line is because these points are not really plotting on the on the isochrone itself, right? So that's why you need to have arbitrary points in between to find out the gradient. And then what I was discussing about this question, where you have the link also to the isoplot. This is done through isoplot, but I suggest you to do using the manual method with the graph sheet, and calculate the age of the rock, and also the initial isotope ratio. Don't worry about the uncertainty of the age. Uncertainty of the age you don't want to uh, worry, because it is it can be calculated by the program, Excel program only, right? So you can see here the age is given, sorry, the slope is given, and the uncertainty is also given, plus or minus value, right? These are given by the software or the program, so you can't manually do that. That's the disadvantage we have when doing manual. There are methods to do very complicated mathematical approaches are there, but it takes long time, and we don't need to do that once we have these softwares now. But you have to do the manual plotting for this data, and most probably you will get a very good isochron, because you see here, according to the program plotted ones, they are plotting exactly on the same line. Regression line is the same, so you might also be able to draw the best fit line using along all these points, right? So in that case, the age should be very precise. So you use some intermediate arbitrary points to get the m calculated, or the gradient calculated, and to calculate the age. Initial ratio can be given from here. Okay, so I will share this document, so you can try with a graph sheet this question number 6. Okay, right. Okay. Right, so we can now leave, we can now stop the meeting, and I hope you will have a good success in the exam.